Hello, my name is Ryan Ridgely, and Jeremiah and I were the discussion board leaders for week 15. And in this week's discussion, we used parametrization to answer some questions about some position vectors, and these position vectors represent the bugs in the story. So let's just get to question 1. Where does each particle start? So in order to find where each particle starts or each bug starts, we just set t equal to 0 and we solve for these vectors. And when we do that, we get r equals 1, 2, r2 equals negative 3, 2, and r3 equals negative 3, 1.5. You can also do that by plotting these vectors and just setting t equal to 0. So you can do that also. So if we do that here, we see exactly where each one of these vectors starts. And then for question 2, we're looking at where these bugs are moving. So there's a couple ways you could do this. The way I did it was I just solved for the derivative. And when you solve for the derivative, you get r1 equals negative 2, negative 4. r2 equals negative 4t, 3t squared, and r3 equals 6, negative 3. Now you can also go back to your plot here and just get a general idea by sliding t. So right here, we see exactly the direction they're going in. Now R1 is going to be going to the southwest direction. R2 is going to be going to the northwest, and R3 is going to the southeast. You can see that as I vary t, and you can see what direction they're going in. So the next question, will any of these bugs come into contact? Well, we can see here that they definitely do. By visualizing, we see right there R1 and R3 are going to cross at the origin. Now we can see that t is going to equal 0.5 at that moment. You can also answer this question by setting the components of the vectors equal to themselves and then solve for t. And if t equals the same value for each component, then you know that they are going to cross at that time. But if t were to equal different, for their x and the y component, then they don't cross at that time. So this is how you can do it mathematically, and this is a way to visualize the answer. Okay, so are any of these bugs standing still at any given moment? Well, we found the velocity of each one of the vectors. So because R1 and R3, their velocity is constant, it's never going to be standing still at any given moment. However, R2 varies. So what we can do is we can take that vector and we can set it equal to 0 and then see exactly when t equals 0. In this case, that it is 0. 0 is the answer, so it is standing still as right when it starts. Alright, so now we're looking at how fast each bug is traveling. So this is going to be related to magnitude. So R1 is going to equal the square root of the sum of the vectors components squared. So R1 has a speed of 4.47 meters per second. R2 varies, so R2 is just going to be a function because it changes over time, right? So that's going to be the square root of 16t squared plus 9t to the 4th power. And R3 is going to have a constant speed of 6.7 meters per second. Okay, so do any of the bugs have the same speed at any given moment? Well, we know that the speed for R1 and R3 are constant and they're different, so they're never going to be equal. However, R2 changes. Therefore, there must be a time at which the speed is equal to each one of those other vectors. And we can figure that out by setting this equation, the magnitude for R2, equal to the magnitude of R1 and R3. So we see here that we set the square root of 16t squared plus 9t to the fourth equal to 6.7. And we see that at t equals 1.23 seconds, those magnitudes are going to be the same, so they're going to be traveling at the same speed. Same thing with R2. Set that equation equal to 4.47, and we see that t equals equals 0.92 seconds. All right, so this brings us to the next question: perpendicular vectors. So we have been doing this for a long time. We know that the dot product of two vectors, if the dot product equals 0, then they are perpendicular to each other. So we just set R1 and multiply that by R3, and we can see that it indeed equals 0. Therefore, they are perpendicular. Are any of the bugs accelerating? Well, in order to figure that out, we just need to find the derivative of the velocity vector. So when we do that, we actually don't get anything for R1 and R2 because their speed, their velocity is not changing. Therefore, it's not accelerating, it's not decelerating. It's just moving at a constant rate. However, vector R2 is accelerating because it changes. So we take the derivative of that vector and we get negative 4/6t. Therefore, we know that R2 is accelerating. All right, and that's it. If you guys have any questions, you can send me a message on Canvas, and I hope everyone has a good weekend.